In 2017, an astrophysicist walked into the office of a NASA climate scientist to talk about life on other planets. The climate scientist listened for a while, then asked, almost casually, "How do we know there wasn't one here?" The two of them sat with that question for a long time. They wrote a paper about it. And the paper, when you read it carefully, does not say what most people think it says. It says, the geological record cannot rule out a prior civilization on Earth. Not Atlantis. Not aliens. Something much stranger. So pour yourself something warm, dim the lights, and settle in. We are going to follow that question all the way to where it actually leads. Part 1. The two scientists who couldn't rule it out. Sometime in 2017, an astrophysicist named Adam Frank walked into the office of a climate scientist named Gavin Schmidt at the NASA Goddard Institute for Space Studies in New York. Frank wanted to talk about exoplanets. He wanted to talk about how a civilization on another world, hundreds or thousands of light years away, might be detectable through the chemical fingerprints it left in its atmosphere. He had been thinking about it for years. He had a framework. He was excited. Schmidt listened. And then Schmidt asked him a question that, by Frank's own later account, briefly broke the conversation. He asked it casually, the way someone might ask whether you want sugar in your coffee. He said, "Wait, how do we know there wasn't one here?" The question hung in the room. Frank had not expected it. Schmidt had not been planning to ask it. But once it was out, it could not be put back. The two of them sat with it for a moment, and then they started talking about it seriously, and that conversation turned into a paper, and that paper turned into one of the strangest pieces of peer-reviewed scientific literature published in the last 20 years. The paper appeared in 2018 in the International Journal of Astrobiology under the title The Silurian Hypothesis. The name is a joke, although it hides a real problem. The Silurians, in the original sense of the term, are not a real species. They are characters from the British science fiction series Doctor Who, a sapient reptilian people who established an advanced civilization on Earth long before humans, then retreated underground to sleep through the ice ages. The name is a wink. The authors knew the name was a wink, but the question the paper actually asks is not a wink at all. The question is this: if a technologically advanced civilization had existed on Earth at some point in the far past, millions of years before us, would we be able to tell? Could we find evidence in the geological record? Could we distinguish their fingerprints from natural processes? Could we rule them out? The answer the paper reaches, after about 10 pages of careful analysis, is not a confident no. It is something much more uncomfortable. The answer is that direct evidence of a prior industrial civilization, in the form of artifacts or bones or buildings, would almost certainly not survive over geological timescales. The evidence that might survive would be chemical and isotopic, and even those signatures could be confused with natural events. And the most honest reading of the data is that we cannot rule out the existence of one or more prior civilizations on Earth, somewhere in the distant past, on the basis of the rock alone. I want to be careful here, because the way this paper has been misquoted by alternative history websites and ancient aliens documentaries would make both authors wince. Schmidt and Frank have publicly stated, in interview after interview, that they personally do not believe a prior industrial civilization existed. They wrote the paper as a thought experiment, partly as a serious analysis and partly as a tool for thinking about how to search for civilizations on other planets. The point of the paper is not to claim that anyone was here. The point of the paper is to investigate the limits of what the geological record can tell us. But the limits, when you actually examine them, are interesting. The limits do not say what the average person might assume they say. They do not say that if a civilization had existed, we would definitely have found evidence. They say almost the opposite. They say that the absence of evidence is not, in this case, evidence of absence. It is just absence. And absence, by itself, does not tell you what was there. So we are going to spend the next 2 hours walking through this question with the patience it deserves. We are going to look at the actual chemical and isotopic fingerprints a civilization would leave behind. We are going to look at the one event in the far past where most of those fingerprints actually appear in the rock, at roughly the right scale, with an explanation that is almost certainly natural. We are going to look at the recent argument about whether our own civilization, the one currently in operation, has produced a sufficient stratigraphic signature to qualify as a geological epoch. We are going to look at the closer in time version of the question, the one about lost human civilizations and the Younger Dryas and the comet that may or may not have hit. We are going to look at Karahan Tepe and Göbekli Tepe and what they tell us about what real lost civilization evidence actually looks like. And we are going to look at the far past window, the hundreds of millions of years in which the question is even physically possible, and what was living in that window, and whether any of it could have built anything. And then we are going to do something at the end that I want you to brace for, because it is the part that turns the question inside out. We are going to ask what we ourselves are going to leave behind. What a future intelligence, 100 million years from now, would find if they came looking for us, whether they would conclude we existed, whether the answer is yes, whether the answer is no, whether the answer is, in any meaningful sense, knowable. The question we are walking into is not whether anyone was here. The question is whether we would know if they had been. Those are not the same question. They are not even close. And the difference between them is the entire reason this video exists. I want to tell you a little more about the personalities involved, because the people who wrote this paper are not what most viewers might assume. Gavin Schmidt is, by training and reputation, one of the most quantitatively careful climate scientists alive. He has spent decades modeling atmospheric chemistry and ocean dynamics. His work involves matching observational data to computational models, refining the models, and being very honest about what the data does and does not show. He is not someone who casually entertains speculative claims. When he says he doubts a prior civilization existed, that doubt comes from a deeply skeptical mind that has spent its career resisting the temptation to overinterpret data. When he allows that the question is non-trivial, that allowance comes from the same place. Adam Frank is a different kind of scientist. He is an astrophysicist who has spent much of his career thinking about how the conditions for technological civilization arise on planets, what energy budgets sustain those civilizations, and what fingerprints they leave on their stars and atmospheres. His work on technosignatures, the chemical and physical evidence of advanced civilizations that we might detect across interstellar distances, is the framework that the Silurian hypothesis paper applies inward. Frank has written multiple popular books about astrobiology and the search for life elsewhere. He is not, in the popular sense, a fringe figure. He is a working scientist whose research happens to touch on questions most scientists never ask. The combination of these two minds, careful climate science and careful astrobiology, is what gives the Silurian hypothesis paper its weight. It is not a paper written by people who want to believe. It is a paper written by people who have professional reasons to want the question to have a clean answer, and who could not, when they ran the analysis, find one. Before we go further, I want to feel the scale of the thing we are about to examine. Because the question of whether a civilization could have existed in the far past and been erased depends entirely on how much time there has been and how briefly we have occupied any of it. So before we get to the chemistry and the rock and the carbon isotopes, I want to spend a few minutes on what the far past actually means, because the far past is not just a long time, it is something else. is less than break time equals 1s, is greater than number, part 2, the 1.2 seconds before midnight. The Earth is 4.54 billion years old. I want you to sit with that number for a moment, because most numbers in popular science get thrown around without anyone really feeling them. 4.54 billion. If you counted to that number, one number per second, without stopping, without sleeping, without ever taking a breath, you would still be counting 144 years from now. Your children would be counting, your grandchildren would be counting. The counting itself would outlast your line. That is how long Earth has been here. 4.5 billion years of slow geological work. Continents forming and dissolving. Oceans appearing and disappearing. Atmospheres remade by living things. Ice ages and warm ages and impacts and eruptions. The kind of stretch of time that the human mind is not really equipped to hold. So scientists, when they want to give people a sense of geological time, sometimes compress all of it into a single 24-hour day. Midnight at the start is the formation of Earth. Midnight at the end is right now. Let me walk you through where things happen on that clock. The Earth forms at midnight. The Moon forms not long after, from a giant impact that happens within the first hour. By around 4 in the morning, the first single-celled life has appeared in the early oceans. Photosynthesis, the process that eventually fills the atmosphere with oxygen, gets going by mid-morning. The atmosphere becomes oxygen-heavy around 2 in the afternoon. Complex multicellular life, the kind of life that has cells specialized into tissues and organs, does not really get going until around 9 in the evening. The Cambrian explosion, the moment when complex life suddenly diversifies into every major animal body plan, happens just after 9 o'clock at night. Plants colonize land at around 10 in the evening. The first vertebrates climb out of the ocean shortly after. Dinosaurs appear at 10:24 p.m. They dominate the Earth for the next 87 minutes of clock time. Mammals are around the whole time, but they are small, mostly nocturnal, and they stay that way until 10:39 p.m., when the asteroid hits the Yucatan Peninsula and the dinosaurs vanish. The whole genus Homo, the whole human lineage, from our earliest hominid ancestors to us, appears in the last 30 seconds of the day. Anatomically modern humans appear in the last 5 seconds. Recorded history, the part of human existence with kings and pyramids and writing, occupies the last 1/10 of 1 second. And the industrial era, the 250 years during which we have burned coal and oil and gas, built cities of concrete and steel, sent radio signals into space, and made plutonium that did not previously exist on Earth, occupies roughly the last 1.2 seconds before midnight. 1.2 seconds. That is the entire window during which a human industrial civilization has existed, on a clock that compresses the age of the planet into 1 day. Everything you have ever known, every book ever written, every song ever recorded, every photograph ever taken, every television show, every war, every president, every relative you have ever met. All of it. 1.2 seconds. I want you to feel that ratio for a second, because the question we are exploring depends on it entirely. If technological civilization is something that happens occasionally on a planet like Earth, given enough time, then the relevant question is how much time there has been. The window in which a civilization could, in principle, have existed and then been erased by geological time is not the entire 4.5 billion years. It is bounded at the bottom by the availability of fossil fuels, which we will get to. The functional window is roughly the last 350 million years since the Carboniferous coal forests laid down the carbon that an industrial civilization would need. 350 million years. That is the window. Humans have had 250 of those years. The ratio of our occupation of the window to the size of the window is roughly 1 to 1.5 million. We are an absolutely tiny presence inside an enormous, slowly turning, gradually erasing planetary system. And the question of whether we are the first is not the question of whether someone else has done what we have done. It is the question of whether someone else could have done what we have done, and then disappeared so completely that the rock no longer remembers them. So, when I tell you, in the next part, that the geological record cannot easily preserve a 250-year industrial blip across 60 million years of subduction and erosion, I want you to already have a feeling for what those numbers mean. They are not abstract. They are the size of the question. And the question, as Schmidt and Frank discovered, is much bigger than the answer. There is another way to feel the scale of this, and I want to spend a moment on it before we move on, because I think it helps. The deepest hole humans have ever drilled into the Earth is called the Kola Superdeep Borehole in the Murmansk region of Russia, near the Norwegian border. The Soviet Union began drilling it in 1970 and continued through 1992. The deepest point reached was 12,262 meters below the surface. That is just over 12 kilometers. The drill broke through ancient continental crust, encountered higher temperatures than expected, and eventually had to stop because the rock at depth was effectively plastic at the heat the drill encountered. 12 kilometers sounds like a long way until you realize that the average thickness of continental crust on Earth is about 35 kilometers. The Kola borehole reached about 1/3 of the way through the crust beneath one single location on the planet. We have explored less than 1/3 of 1% of the volume of the upper continental crust in one place. The enormous majority of the planet's geological record is, in a literal sense, beneath what we have ever directly examined. When you combine this with the recycling of the ocean floor and the slow erasure of the continents by erosion and uplift, what you have is a planetary memory that we are sampling only at the surface, only in places that have not been recycled, and only with the methods available to early industrial era technology. The completeness of the geological record, from a sampling perspective, is much lower than the textbooks suggest. Most of what has happened on Earth is, very simply, not available to us. We are reading the available pages of a book whose binding has been chewed by time, and most of the chapters are missing, and the chapters we have are stained and unevenly inked. What would it actually take to make a civilization disappear completely? Not partially, not mostly, completely. The honest answer is more interesting than you would think, and less reassuring is less than break time equals 1s, is greater than number. Part 3. What a civilization would have to do to disappear. To make sense of why a prior civilization might be invisible to us, you have to start with a fact about Earth that gets very little attention in popular science, even though it is one of the most consequential facts about the planet we live on. Earth is the only known terrestrial body in our solar system with active plate tectonics. It is the only one whose surface is constantly being recycled. Mars stopped moving its plates billions of years ago and is now geologically frozen. Venus appears to have a stagnant lid, with periodic global resurfacing events, but no continuous tectonic motion. Mercury is geologically dead. Only Earth is still rearranging itself, year after year, century after century, era after era. The mechanics of this recycling are slow but relentless. At places called convergent margins, where two tectonic plates meet, the denser plate is forced beneath the lighter one and dragged down into the mantle. This process is called subduction. The plate that gets dragged down is heated, compressed, partially melted, and eventually absorbed back into the convecting material of the planet's interior. The oldest oceanic crust currently on the surface of Earth is in the western Pacific. It is about 180 million years old. Everything older than that has already been pulled under and destroyed. Think about what this means. 65% of Earth's surface is ocean. Almost all of that ocean floor is younger than the KPG extinction event that killed the dinosaurs. The other 35%, the continental crust, is older on average, but it has been weathered, eroded, uplifted, redeposited, and metamorphosed many times. The rocks beneath your feet right now have stories you cannot reconstruct. Most of the surface that existed 300 million years ago is gone. Burned, recycled, mixed back into the mantle, and remade into new rock. Continental erosion happens by other mechanisms. Rain falls, water seeps into cracks. Freeze and thaw cycles widen those cracks. Wind carries away small particles. Glaciers grind across the surface, polishing it like sandpaper. Mountains that stood as tall as the Himalayas have been ground flat in tens of millions of years. The Appalachian Mountains in eastern North America were once a range comparable in scale to the modern Alps. Time has reduced them to rolling hills. Time always wins. Time is patient. Now consider what happens to the materials of modern civilization in this kind of environment. Concrete, which we use to build essentially every modern structure, is a mixture of cement, sand, gravel, and water. Cement reacts with carbon dioxide in the air and slowly carbonates. Concrete weathers, cracks, spalls, and crumbles. Estimates of how long an abandoned concrete building would persist in temperate conditions range from a few hundred to perhaps a few thousand years before significant structural failure. Reduced to gravel, it might persist as identifiable material for a few 100,000 more. Beyond that, it is indistinguishable from natural sediment. Steel corrodes. Without active maintenance, exposed steel rusts at a rate that varies with humidity and salt content, but a steel beam in normal atmospheric conditions will be reduced to flakes within a few centuries. Buried steel lasts a bit longer, but eventually dissolves into iron oxide stains in the surrounding soil. Within 10,000 years, the original shape is gone. Within 1,000,000, the chemical anomaly itself has dispersed. Aluminum, despite being more reactive than iron, forms a protective oxide layer that slows its corrosion. But unprotected aluminum still degrades over geological time. Within a few million years, even the aluminum is gone. Plastics last longer in some forms than others. Polyethylene and polystyrene can persist as molecular fragments for an extremely long time, possibly tens of millions of years, but the objects they once formed will have broken down into microparticles and then into chemical residues. The cities are gone. The chemistry remains. Now consider the fossil record paradox. Homo erectus, our closest extinct human relative, lived for approximately 1.5 million years. The species was widely distributed across Africa, Europe, and Asia. Homo erectus used fire, made stone tools, hunted in coordinated groups, and migrated across continents. There were probably tens of millions of Homo erectus individuals over that 1.5 million-year span. How many of them left fossils that we have found? In the entire history of paleontology, the total number of identifiable Homo erectus specimens is in the low thousands. A species that lasted 6,000 times longer than recorded human history left a fossil record that fits comfortably into a few museum cabinets. This is not unusual. This is normal. The fossil record is the exception, not the rule. Most organisms that ever lived left no fossil at all. Most species that ever existed have left no trace. The geological record is not a library, no matter what your high school textbook might have suggested. It is a curated, edited, abridged, incomplete, and mostly missing draft. The pages are torn out, the chapters are jumbled, the dates are smeared. What survives is the exception, not the average. Apply this to a hypothetical prior civilization. If it lasted for 250 years, the way our industrial civilization has so far lasted, the chance that any direct artifact survives 60 million years of plate tectonics, erosion, and sedimentary cycling is essentially zero. If it lasted 10,000 years, the chance is slightly better, but still negligible. If it lasted 1,000,000 years, you might have one or two preserved artifacts somewhere, in some sedimentary basin that happened to escape recycling, but you would have no way to recognize them as artifacts unless you knew exactly what you were looking for. Even bones decay. A buried human skeleton, in average conditions, lasts a few 100,000 years at most before the calcium phosphate of the bones is fully replaced by mineral substitutes or dissolved away entirely. The fossils we have of much older organisms exist because of unusual preservation conditions. Anoxic mud, rapid burial, mineralization, tar pits, volcanic ash. The enormous majority of bones from any species ever did not get those conditions, and so the great majority of bones from any species ever are not preserved. What this all means is this: a civilization that lived even very recently in geological terms could have left almost no trace at all. A civilization that lived in the far past, 60 million years ago, 200 million years ago, 300 million years ago, would have left effectively nothing direct. No buildings, no bones, no artifacts. The buildings would be gone, the bones would be gone, the artifacts would be gone. We are not going to find ruins from the late Cretaceous because there are no ruins left to find. Whatever was built was unbuilt by the planet a long time ago. But there is something that survives, something subtle, something that the rock holds on to, sometimes, when it has held onto nothing else. The chemistry of what a civilization burns, builds with, refines, and discards leaves traces in the sediment that can persist far longer than any physical object. The chemistry of a civilization is its longest-lasting fossil. And the chemistry of a civilization is what we would have to look for if we wanted to find one. Which brings us to the question of exactly what those chemical signatures look like. Because the strange thing is, we know what to look for. We know it precisely. We know it from our own civilization. We can describe the fingerprint we ourselves are leaving in the sediment, and that means we know the fingerprint we would have to find in older sediment if we wanted to detect someone like us. The next part is the catalogue of what we would be looking for, and one item on that catalogue is going to make this entire video stranger than you expect. Is less than break time equals 1s, is greater than number part 4. The chemical fingerprints we'd look for. Here is the central insight of the Silurian hypothesis paper. Because direct artifacts will almost certainly not survive geological timescales, the only realistic way to detect a prior industrial civilization is through chemical and isotopic anomalies preserved in sedimentary rock. The question is what those anomalies would look like, how distinct they would be from natural processes, and how confidently we could identify them after tens of millions of years. The first signature on the list is the most important. It is the carbon isotope excursion. Carbon, the element that makes up the foundation of life and the bulk of what we burn for energy, has two stable isotopes. Carbon-12 is the lighter and more common form. Carbon-13 is the heavier and rarer form. Plants, when they photosynthesize, preferentially incorporate carbon-12 into their tissues because the lighter isotope is easier to process at the cellular level. This means that organic matter and the fossil fuels that come from buried organic matter is enriched in carbon-12 relative to the atmosphere. When you burn fossil fuels, you release carbon-12 enriched carbon dioxide back into the atmosphere. The result is a measurable drop in the ratio of carbon-13 to carbon-12 in the atmosphere, in the oceans, and eventually in the sedimentary record. Scientists call this ratio the delta carbon-13 value, and it is one of the most reliable proxies for understanding ancient climates and chemistries. A sharp, sustained, planet-wide drop in the delta carbon-13 value is exactly what you would expect to see from a fossil fuel-burning civilization. It is also exactly what we see right now in modern sediments. The current rate of delta carbon-13 change is faster than at any other point in the recoverable geological record. We are, in other words, leaving the strongest possible chemical fingerprint of an industrial civilization in real time. We can measure our own ghost. The second signature is reactive nitrogen. Most of Earth's nitrogen exists in the atmosphere as inert nitrogen gas. To be useful to living organisms, that nitrogen has to be converted into biologically usable forms like ammonia, nitrate, or organic nitrogen compounds. Natural processes do this slowly. Lightning fixes a small amount. Specialized bacteria fix more. The total natural rate of nitrogen fixation on Earth is bounded by the rate at which these biological processes can operate. Then, in 1909, a German chemist named Fritz Haber figured out how to fix nitrogen industrially, using high pressure, high temperature, and an iron catalyst. The Haber-Bosch process now produces more reactive nitrogen each year than all natural processes on Earth combined. The result is that the global nitrogen cycle has been profoundly altered. Soils contain more nitrogen than they otherwise would. Lake sediments record nitrogen anomalies. The signature is global and synchronous. The third signature is long-lived radionuclides. The atmospheric testing of nuclear weapons in the 1940s, 50s, and 60s scattered radioactive isotopes across the entire planet. Some of these isotopes have short half-lives and have already decayed. Others have very long half-lives. Plutonium-239 has a half-life of about 24,000 years. That means that 24,000 years from now, half of the plutonium-239 we have created will still be detectable. Plutonium-244 has a half-life of about 80 million years. The plutonium-244 signature, in principle, could persist as a detectable fingerprint for hundreds of millions of years. There is no natural source of plutonium-239 or plutonium-244 in the modern Earth. Both are produced by neutron capture on uranium-238, which happens in nuclear reactors and in nuclear weapons. The presence of either isotope in significant quantity in a sedimentary layer would be a clear marker of a technological civilization. The fourth signature is synthetic organic compounds. Plastic is the most famous example, but the larger category includes every petroleum-derived chemical we manufacture and release into the environment. Pesticides, pharmaceuticals, industrial solvents, refrigerants, lubricants. Many of these compounds do not exist naturally. Their molecular structures are arranged in ways that natural chemistry does not produce. If a sediment layer contains these compounds in detectable quantity, the source must be industrial. The fifth signature is heavy metal anomalies. Civilizations mine and refine specific metals at scales that are not natural. Lead, copper, mercury, zinc, the rare earth elements. The geographic distribution of these metals shifts when humans extract them from concentrated ore bodies and disperse them through industrial use. Lead in particular shows up in the geological record as a precise marker. Greenland ice cores show lead pollution from Roman silver smelting 2,000 years ago. The lead signature from leaded gasoline in the 20th century is even sharper. The sixth signature is species redistribution. A civilization that domesticates animals and plants moves species around in patterns that natural biogeography cannot produce. A future paleontologist looking at the late Holocene sediments would find anomalous concentrations of certain species in places they have no natural reason to be. Chickens on every continent, cows on every continent, wheat pollen far outside the Fertile Crescent. The biogeographical signature of agriculture is global and distinct. The seventh signature is sediment composition itself. Fly ash from coal combustion produces glassy spherules of a characteristic chemistry that show up in sediment cores as a clear marker. Microplastics distribute through marine and terrestrial sediments globally. The carbon to nitrogen ratio of sediment shifts in industrial layers in ways that natural decomposition does not produce. Now here is the uncomfortable observation. Every single one of these signatures, separately, is something that natural geological processes can also produce, at least sometimes at smaller scales. A volcanic event can produce a carbon isotope excursion. A natural bacterial bloom can shift nitrogen ratios. Background radioactive decay can produce trace anomalies. Volcanic glass can look superficially similar to fly ash. Heavy metal concentrations can occur naturally near ore bodies. The signal of an industrial civilization is the combination of these markers, appearing together, globally, synchronously, at the right ratios. It is the constellation, not any single star. And the constellation, in principle, should be unique enough to distinguish from any natural process, in principle. But here is where the story gets uncomfortable. There is one event in the far past, 56 million years ago, where most of the chemical markers of a fossil fuel burning civilization show up in the sedimentary record at roughly the right scale, in the right ratios, in the right timing. The mainstream scientific explanation for this event is natural. Schmidt and Frank, in their paper, are careful to call it almost certainly natural. The almost is doing a great deal of work. The event is called the Paleocene-Eocene thermal maximum. Before we go there, I want to add one more observation about the chemical fingerprints, because it matters for what comes next. The signatures we have just walked through are not just a list of things we expect from a civilization. They are a list of things we expect from a civilization that resembles ours in particular. A civilization with a different energy base might produce different signatures. A civilization that relied primarily on biofuel, for example, might leave a sharp carbon isotope excursion, but no significant radionuclide trace. A civilization that used a form of energy we have not yet invented, perhaps something based on geological heat extraction at scales we cannot currently achieve, might leave subtle thermal anomalies in the rock that we would not currently know to look for. A civilization that built primarily with stone and biological materials, even if it had advanced knowledge, would leave essentially no industrial signature at all. This last possibility is worth holding on to. There is no law of physics that says a complex civilization must burn fossil fuels. There is no requirement that intelligent beings must follow exactly the developmental trajectory that humans followed. The chemical fingerprints we look for are the fingerprints of a specific kind of civilization, the kind we ourselves are. A non-human prior civilization might have been very different in its energy choices, its material choices, its development pattern. Such a civilization might be effectively invisible to our methods, not because the rock failed to record it, but because we are not looking for what it would have left. This is part of why the Silurian hypothesis paper is more careful than the popular summaries of it admit. The paper does not just ask whether a civilization like ours could be hidden. It asks whether any civilization at all could be detected, given the kinds of evidence the rock actually preserves. The answer to the first question is uncertain. The answer to the second is closer to no. The next part is the strangest case the geological record offers us, and I want to be very clear before we get there. I am not telling you the PETM was caused by a prior civilization. I am telling you that the PETM is what a natural event that mimics a civilization looks like, and the resemblance is close enough that two careful scientists, in a peer-reviewed paper, felt the need to discuss it explicitly. Is less than break time equals 1s is greater than number part 5. The strange case of the PET. Approximately 55.8 million years ago, the world changed quickly. The exact dating depends on the method, but the consensus is tight. The boundary between the Paleocene and Eocene epochs is marked in sedimentary cores all around the world by a sudden, sharp, planet-wide event called the Paleocene-Eocene thermal maximum. Geologists call it the PETM, and the PETM is, by some margin, the closest analogue in the ancient geological record to what humans are doing to the climate right now. Let me set the scene. 55.8 million years ago, the dinosaurs had been gone for about 10 million years. Mammals had begun to diversify into the body plans we recognize today. The continents were arranged differently from now. Greenland and northern North America were warmer. Antarctica was not yet covered in ice. The Atlantic Ocean was narrower. The global climate was warmer than today, but stable. Then, over a relatively short geological interval, the climate jumped. Global average temperatures rose by between 5 and 8 degrees Celsius. Tropical conditions extended to high latitudes. Sea levels rose, ocean chemistry shifted. The oceans acidified, killing off entire communities of abyssal organisms and causing major changes in surface marine ecosystems. Carbonate sediments dissolved on the sea floor. Mammals on land migrated, shrank in average body size, and reorganized into new ecological communities. Many species went extinct. Many new species evolved. The cause of the PETM was a massive injection of carbon into the ocean atmosphere system. The estimates vary, but the most commonly cited range is roughly 2,000 to 7,000 gigatons of carbon released over a period of several thousand years. To give you a sense of scale, humans have released approximately 2,000 gigatons of carbon since the start of the industrial era. The PETM was larger in absolute terms, but slower. The rate of human emissions is faster than the rate of PETM emissions, possibly by an order of magnitude. We are doing in 2.5 centuries what nature did in several thousand years. The carbon injection at the PETM left a clear fingerprint in the rock. The delta carbon-13 value, the ratio of carbon-13 to carbon-12, dropped by about 3 to 5 parts per thousand. This is a large, sharp, globally synchronous negative carbon isotope excursion. It is exactly the kind of signal that a fossil fuel burning civilization would leave behind. It is also exactly what we would expect from any large injection of biologically derived, isotopically light carbon into the atmosphere. The mainstream explanation for the PETM has 2 leading candidates. The first is massive volcanic outgassing from the North Atlantic Igneous Province, a region of intense volcanic activity during the opening of the modern North Atlantic. The volcanism injected enormous quantities of carbon dioxide directly into the atmosphere, with isotopic signatures consistent with mantle-derived carbon. The second candidate is destabilization of methane hydrates on the sea floor. Methane hydrates are ice-like cages of water molecules that trap methane gas, formed under conditions of high pressure and low temperature. They are stable at the cold, high-pressure environment of the abyssal ocean floor. If the abyssal ocean warms even a little, the hydrates destabilize and the methane is released into the water column, where some of it eventually reaches the atmosphere. Methane is isotopically very light, much lighter than even fossil fuel carbon, which would explain the magnitude of the carbon isotope shift. Most current models combine these 2 explanations. Volcanism started the warming, which triggered hydrate destabilization, which amplified the warming, which triggered more hydrate destabilization in a runaway loop. The full event lasted about 200,000 years before the system slowly returned to baseline. Now here is what I want you to sit with. The chemical signatures of the PETM, taken individually and in combination, look uncannily like what a planet would experience if a major industrial civilization burned through its accessible fossil fuel reserves over a period of a few thousand years. Carbon isotope excursion, temperature spike, ocean acidification, species turnover, atmospheric chemistry shift. The match is not exact, and there are important differences, but the resemblance is close enough that Schmidt and Frank specifically address the PETM as a case study in their paper. They are careful. They do not claim the PETM was caused by a civilization. They say the PETM is almost certainly natural. They cite the volcanic and methane explanations as the most likely. But they note that the PETM shows us what a natural event that mimics an industrial signal actually looks like in the rock. And they note that distinguishing the PETM from a hypothetical industrial event on the basis of the sedimentary record alone would be difficult. What is missing from the PETM, what we would expect to see if it were industrial, is microplastics, synthetic compounds, plutonium, heavy metal anomalies in the patterns mining produces. The PETM has the chemistry of carbon and temperature. It does not have the chemistry of industry. So the PETM, on careful examination, is probably not a civilization signal. But here is the kicker. Plastic and synthetic organic compounds did not exist before the 20th century. Plutonium did not exist before the 1940s. If a prior civilization had existed in a different stage of technological development, one that burned fossil fuels but had not yet developed plastics and nuclear technology, what would distinguish its signature from a natural carbon spike? Possibly nothing at all. This is the part of the Silurian hypothesis that is genuinely uncomfortable to sit with. Not because there is evidence for a prior civilization, there is not. The PETM is almost certainly natural, but because the line between natural and artificial in the ancient sedimentary record is thinner than our scientific intuition wants it to be, because the chemistry of a civilization in its early industrial phase would be hard to distinguish from a volcanic and methane release event, because if we are looking for ourselves in the distant past, we cannot easily tell ourselves apart from a planet doing what planets sometimes do. There are other warming events in the far past. The Eocene thermal, maximum 2, smaller than the PETM, but similar in shape, about 53 million years ago. The early Eocene climatic optimum, a sustained warm period from about 53 to 49 million years ago. Each of these shows carbon isotope features at smaller magnitudes than the PETM. The pattern of warming combined with isotope shift is not unique to the PETM. It is a recurring shape in the rock. I want to put this in scale before we move on. The PETM lasted approximately 200,000 years. Our entire industrial era has lasted approximately 250 years. The signature of the PETM in the rock spans a thick layer of sediment that geologists can identify with confidence. The signature of our era, if it were buried and the planet looked back at it from 50 million years in the future, would be a thin layer about the thickness of a fingernail. I want to mention one more uncomfortable thing about the PETM before we move on. The biological consequences of the event lasted long after the temperature returned to baseline. Many species that went extinct at the PETM never reappeared. The mammals that survived the warming and reorganized into the post-PETM world were on average smaller than their pre-PETM ancestors, a phenomenon paleontologists have documented in detailed fossil collections from the Bighorn Basin in Wyoming and other key PETM sites. The shrinkage of mammal body size during sustained warming is real, observable in the fossil record, and predictable from physiological models. If a future paleontologist found a similar pattern in our own future fossil record, they might infer a global warming event. They might or might not consider whether the warming had been caused by a civilization. What this all means, when you sit with it, is that the PETM is not just an analogue to anthropogenic climate change in a thermodynamic sense. It is an analogue in a much larger sense. It is the kind of geological event that, if you walked into it without any other context, you might or might not be able to distinguish from an industrial era. The signature is the right shape. The duration is the right order of magnitude. The biological response is the right pattern. The only difference, as far as we can tell, is the absence of the specifically synthetic chemistries that postdate the development of industrial chemistry on Earth. And those chemistries are recent enough that they would not have been part of an earlier civilization's signature if such a civilization had existed before our materials science had been developed. The PETM teaches us that natural events can look like civilizations. The next case teaches the opposite. The next case shows how a natural process can look so much like a civilization that, for a brief moment, in the 1970s, some scientists openly considered whether they had found the work of one. The case is from a uranium mine in Gabon, and it is one of the strangest stories the 20th century told. Is less than break time equals 1s, is greater than number. Part 6, Oklo, and the day we found the wrong reactor. In 1972, at a uranium processing facility in southern France, a technician named Henri Bouzigues was running routine quality control checks on a shipment of uranium ore that had arrived from a mine in the Gabon region of West Africa. The ore was supposed to be ordinary. Every shipment of natural uranium that had ever been processed anywhere in the world contained the same ratio of uranium-235 to uranium-238. That ratio is set by the radioactive half-lives of the two isotopes, which are constants of nuclear physics. Natural uranium today is about 0.72, 0% uranium-235, with the rest being mostly uranium-238, regardless of where the ore comes from. Except this shipment had less uranium-235 than it should have, not much less, about 3 parts per 10,000 less, but enough that the mass spectrometer flagged it as anomalous. And anomalous, in the world of nuclear materials, is a serious word. The only known process that depletes uranium-235 from natural uranium is fission. Uranium-235 is what fuels nuclear reactors and nuclear weapons. When it absorbs a neutron, it splits, releasing energy and more neutrons in the process. The natural concentration of uranium-235 in raw ore is the upper limit of what should ever appear. The ore from Gabon was below the lower limit. The implication, in those first hours of confusion, was that someone had already burned this uranium in a reactor. The French facility ran additional tests. The depletion was real. The samples were retested by independent labs. The depletion was confirmed. For a brief, strange moment, the scientific community had to consider the possibility that they had found evidence of a previously unknown nuclear program, or more wildly, that the uranium had been depleted by some process so unusual that no one had yet identified it. There were, in those first weeks, scientists who quietly, half-jokingly, raised the possibility that the ore was the leftover fuel of a prehistoric reactor built by a civilization that had not yet been discovered. The actual explanation, when it came, was almost as strange as the alternative. A team of physicists worked backwards from the anomaly to figure out what process could have produced it. The answer required them to go back 2 billion years. 2 billion years ago, the percentage of uranium-235 in natural uranium was not 0.720%. Because uranium-235 decays faster than uranium-238, the percentage 2 billion years ago was about 3.1%. That is, coincidentally, very close to the enriched fuel grade used in modern commercial nuclear reactors. If you take ore that is naturally enriched to 3% uranium-235 and you concentrate it geologically and you immerse it in groundwater that can act as a neutron moderator, slowing fast neutrons to thermal speeds where they are most efficient at causing fission, you can sustain a slow nuclear chain reaction. That is exactly what happened at Oklo. Approximately 2 billion years ago, at a site in the Oklo region of what is now Gabon, the right combination of conditions came together to produce 17 separate natural fission reactor zones that ran sporadically over hundreds of thousands of years. The average power output of each Oklo reactor was about 100 kilowatts. That is roughly enough to power 1,000 modern light bulbs. The reactors operated in pulses. As the chain reaction heated the surrounding rock, the groundwater would boil away, and the moderator was lost, and the reaction would shut down. As the rock cooled, water would seep back in, the moderator returned, and the reaction would restart. This cycle continued, off and on, for somewhere between 100,000 and 1,000,000 years. Then the geological conditions shifted, the reactors went dormant, and they have been quiet ever since. The implications of Oklo are profound, but not in the way the early speculation suggested. The Oklo reactors are not the work of a prehistoric civilization. They are the work of physics, chemistry, and geology, operating together under conditions that happen to allow what we now know as nuclear fission to occur naturally. The case is the textbook example of an anomaly that looked artificial, that briefly attracted artificial explanations, and that ultimately revealed something even more strange about how the planet works. The meta-lesson is the one I want you to sit with. The line between natural and artificial in the ancient geological record is not a sharp line. It is a line you draw based on the assumptions you bring with you. When the Oklo anomaly was first found, the most parsimonious explanation seemed to be artificial, because the only known process that depleted uranium-235 was fission in a reactor, and the only known builders of reactors were humans. Then someone showed that nature could build a reactor too, and the assumption shifted. The Silurian hypothesis is the formal version of this exact problem, asked at the scale of an entire civilization. If we find a chemical anomaly in the ancient sedimentary record, do we assume natural or artificial? The Oklo case suggests we will tend to assume natural, because natural is what we expect. But the case also shows that we can be wrong in either direction, depending on the surrounding context. 2 billion years ago, a uranium deposit ran for hundreds of thousands of years as a slow nuclear reactor. If we had not been looking for it, we would not have found it. If we had not been able to model the conditions that allowed it, we would not have understood it. And there is no guarantee that we are looking in the right places, at the right scales, for everything the rock might contain. This is the part that gives the Silurian question its real weight. It is not that we have found evidence of a prior civilization and are choosing to ignore it. It is that we may not have found evidence we cannot recognize, because we do not yet have the framework for recognizing it. And, as the next part will show, the framework problem is worse than even Oklo suggests. Because, in March of 2024, the geological community held a vote about whether our own civilization, fully visible, still running, leaving signals in real time, had produced enough of a stratigraphic signature to be officially recognized in the rock. And the answer they reached is the answer that breaks the brain. The next part is the Anthropocene that wasn't, is less than break time equals 1s, is greater than number. Part 7. The Anthropocene that wasn't. In March of 2024, the International Union of Geological Sciences, the body that decides what counts as an official chapter in Earth's geological timescale, held a vote that had been a long time coming. The vote concerned whether the Anthropocene, the proposed new geological epoch defined by human industrial activity, should be added to the official timescale alongside epochs like the Holocene and the Pleistocene. The Anthropocene Working Group, which had spent years preparing the case, had assembled what they believed was overwhelming evidence. The proposed start date was the year 1952, coinciding with the beginning of what climate scientists call the Great Acceleration, the period after World War II, during which industrial output, population growth, resource extraction, and atmospheric chemistry all began increasing at unprecedented rates. The proposed primary marker, the so-called golden spike that would define the boundary, was the global spike in plutonium-239 deposited by atmospheric nuclear weapons testing. Plutonium-239 does not exist naturally on Earth in significant quantities. Its presence in sediment is a clear, synthetic, unambiguous marker. The secondary markers were extensive. Fly ash from coal combustion, present in sediments globally beginning in the late 19th century. Microplastics, distributed across marine and terrestrial sediments worldwide. Pesticide residues, lead from leaded gasoline. The carbon isotope excursion from fossil fuel burning. Nitrogen isotopic anomalies from artificial fertilizer use. Soot from industrial combustion. Stable isotopes of carbon, nitrogen, and oxygen, all shifting in sediment globally and synchronously. The proposed type section, the specific location whose sediment core would serve as the official reference for the new epoch, was Crawford Lake in Ontario, Canada. Crawford Lake is meromictic, meaning its waters do not mix vertically. The bottom of the lake is permanently still. Layers of sediment accumulate in distinct annual bands, like the rings of a tree, preserving the chemistry of the surrounding region year by year. The Crawford Lake core showed the plutonium spike, the fly ash, the microplastics, the carbon and nitrogen shifts, all arriving together within a few years of 1952. The Subcommission on Quaternary Stratigraphy met to vote. The vote was 12 members against, 4 in favour, 2 abstentions. The proposal was rejected. On March 20th, 2024, the rejection was approved by the ICS and ratified by the IUGS. The Anthropocene is not, as of this video, an officially recognised geological epoch. We remain, technically, in the Holocene, the same epoch that began 11,700 years ago at the end of the last ice age. I want you to sit with this for a moment, because it is one of the strangest facts in modern science. We are alive, right now, inside a global civilization that has fundamentally altered the chemistry of the atmosphere, the composition of marine sediments, the distribution of species, the rates of climate change, the patterns of erosion and deposition, the isotopic ratios of carbon and nitrogen and oxygen worldwide. We have synthesized substances that did not previously exist on Earth, and we have spread them globally. We have created radioactive isotopes that have no natural source. We have built cities that are visible from space, and the geological community, looking down at the sediment we are leaving in real time, with all the tools of modern stratigraphy, could not reach a 2/3 majority on whether our signal is strong enough to define a new chapter of Earth's history. The reasons given by the dissenters are technical and worth understanding. Some argued that the proposed start date of 1952 was too narrow, that the case for the Anthropocene as a longer-term phenomenon was stronger than the case for a sharp boundary in the mid-20th century. Some argued that the signature was not yet stable, that human civilization might change in ways that would make the 1952 start date look arbitrary in retrospect. Some argued that the Anthropocene should be classified as a geological event, not a formal epoch, in the same way that the Great Oxidation Event 2 billion years ago is an event rather than an epoch. Some argued that the data, while strong, was insufficient to define the kind of type locality that the geological timescale traditionally requires. There were good arguments on both sides. The vote was not a denial of the human impact on the planet. It was a procedural and methodological conclusion that the specific case being made did not meet the specific standards of the geological timescale. Skelton and colleagues, in a paper published in 2025 in Earth's Future, argued that the case for the Anthropocene as a formal epoch is actually stronger than the case for the Holocene itself, was when the Holocene was first formalized. They argued the rejection was inconsistent with how the timescale has historically been defined. The argument continues, but here is the line I want you to walk out of this part with. Every argument that geologists could not yet officially see our own civilization in the rock is also an argument that they could not officially see a prior civilization in the rock either. The same conservative methodological standards that protect the geological timescale from premature naming also conceal, by definition, anything older than us that would have looked like us. If we cannot reach 2/3 agreement that the current Anthropocene signature is sufficient, with all the markers we have today, with our civilization still actively producing them, then we have no methodological basis to conclude that the absence of similar signatures in older sediment proves no civilization existed. The absence might mean nothing was there. Or it might mean something was there, but its signature, by the same standards we apply to ourselves, would not have qualified. This is the moment in the analysis where the Silurian hypothesis stops being a thought experiment and starts being a serious epistemic problem. We cannot rule out a prior civilization, not because we lack the imagination to look for one, but because the criteria for ruling one in are stricter than even our own civilization can satisfy. The rock is not lying to us. The rock is doing what rock does. We are the ones who do not know how to read it well enough to settle the question. So, where does that leave us? It leaves us, I think, in a strange place where the question is genuinely open and probably unanswerable on the basis of the evidence available. We can build frameworks, we can search for chemical anomalies, we can run mass spectrometry on sediments older than the dinosaurs, but we cannot reach the kind of confident no that our intuition wants. The honest scientific answer to whether we are the first civilization on Earth is we do not know, and we may never be able to know. I want to add one observation about the cultural side of the Anthropocene rejection, because I think it matters for how this video is being received. The argument over whether the Anthropocene should be a formal epoch is not just a scientific argument. It is also a philosophical argument about what kind of mark a civilization makes, and what we want that mark to mean. The dissenters who voted against the proposal were not denying human impact on the planet. They were arguing that the formal geological timescale should be reserved for the kind of large-scale, long-duration, globally synchronous markers that have traditionally defined it. The Anthropocene proposal, in this view, was trying to give a new chapter to a phenomenon that the timescale was not built to record. The phenomenon might be real and important. It might still not be the kind of thing the timescale exists to mark. This is itself a meta-lesson for the Silurian question. The frameworks we have for reading the rock are themselves products of human decisions made by human committees, with human assumptions about what kinds of evidence count and what kinds do not. A civilization that left a different kind of mark on different timescales with different chemistries might be recordable in the rock and still not satisfy the formal criteria for being officially recognized. The rock holds what it holds. The criteria for what counts as evidence are something we choose. And if we choose criteria that exclude the patterns a non-human civilization might have left, we will not find evidence of one, regardless of whether one existed. But there is a closer-in-time version of the question that has been argued, televised, written about, and dramatized for decades. The version that lives at the boundary of mainstream archaeology and popular speculation. The version that says we are not necessarily the first human civilization, that an advanced pre-agricultural society may have existed before 12,800 years ago and been destroyed by a comet impact. The next three parts walk through that closer-in-time version of the title. They walk through the Younger Dryas, through Karahan Tepe, and through Gunung Padang, and by the end of them, you will see how much harder this question becomes the closer you look at it. Is less than break time equals 1s is greater than. Number, Part 8. The comet that may or may not have hit. The Silurian hypothesis asks whether a civilization could have existed in the far past and been erased completely by the slow grinding of the planet. The popular version of "We are not the first" lies much closer in time. It lives at 12,800 years ago, at the start of a sudden cold snap that climate scientists call the Younger Dryas. And the story attached to it is, depending on who you listen to, either a serious scientific hypothesis that has gained increasing support over the last decade, or a piece of speculative pseudo-archaeology that has been amplified by Netflix documentaries to the point where mainstream archaeology has had to spend significant time and energy responding to it. Let me describe the Younger Dryas itself first, because the climate event is real and well documented, even if its cause is contested. Approximately 12,900 years ago, the Earth's climate had been warming steadily for several thousand years as the last ice age ended. Glaciers were retreating, sea levels were rising, ecosystems were reorganizing. The planet was on a trajectory that would eventually lead to the warmer, more stable conditions of the Holocene, the interglacial period during which all of human civilization has developed. Then, very suddenly, the warming reversed. Global temperatures plunged. In some regions, particularly the North Atlantic, temperatures dropped by as much as 10 degrees Celsius within decades. Ice sheets paused their retreat. Forests gave way to tundra. The cooling lasted for about 1,200 years, ending almost as abruptly as it had begun, with temperatures rising sharply again as the Holocene proper got underway. The cause of the Younger Dryas has been debated by climate scientists for more than 70 years. The leading mainstream explanation involves a sudden influx of cold, fresh water into the North Atlantic, possibly from the catastrophic drainage of a glacial meltwater lake called Lake Agassiz that had accumulated on the surface of the retreating North American ice sheet. The fresh water disrupted the thermohaline circulation, the system of ocean currents that brings warm water from the equator to the north, and the disruption produced the cold snap. That is the mainstream explanation. It has been the consensus for most of the last 50 years, but starting around 2007, an alternative explanation emerged, and it is the alternative that has driven the popular narrative. The Younger Dryas impact hypothesis, as it became known, proposes that a fragmented comet or asteroid struck Earth at the start of the Younger Dryas, that the impact and associated effects triggered the climate shift, and that the cataclysm wiped out a number of large North American animal species and possibly devastated human populations across the Northern Hemisphere. The hypothesis was originally based on a layer of sediment, sometimes called the black mat, found at archaeological sites across North America and dated to approximately 12,800 years ago, that contained unusual concentrations of platinum group elements, microspherules of melt glass, nanodiamonds, and other materials consistent with a high-energy impact event. For several years, the YDIH was treated by most mainstream geologists as a fringe hypothesis. Critics argued that the proposed impact crater had not been found, that the chemistry could be explained by other processes, and that the timing of the various proxies did not consistently support a single instantaneous event. The hypothesis bounced back and forth, with new evidence published, then critiqued, then defended. Then, in 2025, 2 papers appeared in the same year that pushed the argument in opposite directions and, in the process, brought the YDIH back into the active scientific conversation. The first paper, published in PLOS One, reported new findings from sediment cores extracted from Baffin Bay, off the western coast of Greenland. The cores were taken from depths between 500 and 2,400 meters below sea level, in waters that had been undisturbed for many thousands of years. The team identified a narrow band of sediment, only a few centimeters thick, dated to approximately 12,835 to 12,735 years before present. Within that band, and only within that band, the team found impact proxies, metallic microspherules, melt glass fragments, platinum group element anomalies, cometary dust particles consistent with carbonaceous chondrite material. The signatures were absent in the sediment layers above and below the band, which the authors argued ruled out a modern, volcanic, or random sedimentary origin. The implication was that something with the chemistry of an extraterrestrial impactor had arrived at Earth in a narrow window of geological time at exactly the moment the Younger Dryas began. The paper was, by the standards of the YDIH, the strongest single piece of evidence yet assembled. The second paper, also published in 2025, came from a team led by the volcanologist Charlotte Green. Green and colleagues had been examining the platinum group element anomalies at other Younger Dryas sites, particularly in Greenland ice cores, where the temporal resolution is much higher than in marine sediment. They found that the platinum spike at the GISP2 ice core began approximately 45 years after the onset of the Younger Dryas cold event, and that the spike lasted approximately 14 years before subsiding. The implications of the Green paper are significant. An instantaneous cataclysmic comet impact does not produce a 14-year platinum plateau that begins decades after the climate shift it is supposed to have caused. The chemistry of the spike, the team argued, was consistent with sustained fissure eruptions at a known volcanic system in Iceland, which would have injected platinum group elements into the upper atmosphere over a sustained period. The volcanic explanation, in their reading, accounted for the timing, the duration, and the chemistry better than the comet hypothesis did. So, in the same year, 2025, two careful papers reached incompatible conclusions about the same body of evidence. The Baffin Bay paper supported a comet impact. The GISP2 paper attributed the platinum to Icelandic volcanism. The science is, as I record this, genuinely unsettled. But the popular version of the Younger Dryas story is much larger than the technical question of whether a comet hit. The popular version says that a globally distributed, advanced human civilization existed before 12,800 years ago, that the impact destroyed this civilization, that the survivors carried fragments of its knowledge into the later cultures of the Holocene, and that the flood myths and creation stories of cultures around the world preserve a real memory of this pre-Younger Dryas civilization and its destruction. This is the version associated with the British journalist and alternative history author Graham Hancock, whose books, beginning with Fingerprints of the Gods in the mid-1990s and continuing through Magicians of the Gods in 2015 and the Netflix series Ancient Apocalypse in 2022, have brought the YDIH to a mass audience. Hancock's broader claim is not just that an impact happened, but that the impact destroyed a sophisticated civilization, and that the existence of this civilization explains everything from astronomical alignments at ancient sites to the global recurrence of flood myths. Mainstream archaeology rejects the underlying claim of a pre-Younger Dryas high-technology civilization. The evidence does not support it. There are no metal tools from before 12,800 years ago. There is no industrial chemistry. There is no settlement infrastructure of the scale that would be expected. The archaeological record of the period shows hunter-gatherer cultures with sophisticated tools and complex social structures, but not the kind of metallurgical and technological development that Hancock's narrative requires. Where mainstream archaeology and Hancock's narrative do partially overlap is on the observation that some pre-agricultural peoples had developed forms of monumental construction and astronomical knowledge that have been historically underestimated. That observation is consistent with the actual archaeological record. The extrapolation to a globally advanced civilization with metallurgy and oceanic navigation is the part that the evidence does not support. So we have, at the boundary of recorded history, a case where the closest in time, best evidenced, most argued version of "we are not the first" remains genuinely unresolved at the technical level and largely rejected at the popular level. Two papers in the same year reach incompatible conclusions about whether a comet hit. A best-selling author argues for a destroyed advanced civilization. The mainstream archaeology rejects the civilization but cannot definitively rule out the impact. And every part of this argument is happening at a scale of 12,000 years, where the sedimentary record is intact, where ice cores resolve individual decades, where carbon dating works reliably, where the evidence should be unambiguous. If we cannot resolve a question at this scale, on this much evidence, with this much instrumentation, then the far past version of the same question, asked across hundreds of millions of years instead of thousands, is harder by many orders of magnitude. Not just harder in principle, harder in a way that may put it beyond the reach of any evidence we could currently collect. But there is one place we have actually found something, one place where the dirt gave up an unmistakable signal of complex human culture before agriculture, before pottery, before writing. It is in southeastern Turkey. It is 12,000 years old. And it is not the lost civilization Graham Hancock describes. It is something stranger, and in some ways more important, because it is real. The next part is Karahan Tepe and Göbekli Tepe. Is less than break time equals 1s, is greater than. Number, Part 9. Karahan Tepe, Göbekli Tepe, and the hunter-gatherers who built temples. In the rolling hills of southeastern Turkey, in a region called the Taş Tepeler, the stone mounds, there is a constellation of archaeological sites that has, over the last 30 years, profoundly changed what archaeologists believe about the origins of human civilization. The two most famous sites in this constellation are Göbekli Tepe and Karahan Tepe. Both date to roughly 12,000 years ago. Both feature massive carved stone monuments. Both were built by people who, by every conventional definition, were hunter-gatherers. Göbekli Tepe was excavated, beginning in the mid-1990s, by the German archaeologist Klaus Schmidt. Schmidt died in 2014, but the excavation continues. The site sits on a hill in southeastern Turkey, and it consists of a series of circular and rectangular stone enclosures built around T-shaped pillars. The pillars are enormous. Some weigh as much as 20 tons. The largest are over 5 meters tall. They are carved from a single piece of limestone, transported from quarries hundreds of meters away, and erected with a precision that requires sophisticated planning and engineering. The pillars are decorated. Some have carvings of animals, including foxes, scorpions, snakes, vultures, lions, and birds. Some have abstract symbols. A few have human figures or human limbs. The T-shape itself appears to be stylized humanoid, with the horizontal top representing a head and the vertical body representing the torso and arms. Multiple enclosures share the same basic design, suggesting a unified architectural tradition across the site. The dating is the most important thing about Göbekli Tepe. Carbon dating of organic material associated with the structures consistently places the construction between approximately 10,000 and 9,500 BCE, that is 12,000 to 11,500 years ago. The site is approximately 7,000 years older than the Great Pyramids of Egypt. It is approximately 6,000 years older than Stonehenge. It is approximately 5,000 years older than the first known cities. Karahan Tepe is approximately 30 kilometers from Göbekli Tepe. It has been excavated more recently, and it may be even older. Some of the structures at Karahan Tepe appear to predate the construction at Göbekli Tepe by several centuries. Karahan Tepe may represent the earliest known village site in human history, with both residential and ritual functions integrated into a single complex of buildings. In October of 2025, archaeologists at Karahan Tepe announced a new discovery: a T-shaped pillar, 1.37 meters tall, made of sand-colored stone, had been uncovered with a carved human face at its top. The face was unlike anything previously found at the site or at Göbekli Tepe. It featured a prominent brow, a straight nose, and sunken eyes carved with sharp, linear precision. The carving is not a stylized symbol. It is a portrait of a specific human face, or perhaps an idealized one. In the same season, archaeologists at Göbekli Tepe found a life-sized human statue embedded horizontally in the base of a wall. The statue had been deliberately placed there, almost certainly as part of a ritual offering when the wall was being constructed. The statue dates to roughly the same period as the original construction, 12,000 years ago. What makes these sites so important is what they imply about the timeline of human civilization. The traditional model held that agriculture was the prerequisite for complex society. The argument was that hunter-gatherers were too mobile, too small in group size, and too constrained by the calorie demands of foraging to develop the kind of large-scale cooperative projects that monumental architecture requires. Settlement, in the traditional model, came after agriculture. Complex ritual came after settlement. Specialized labor came after that. Monumental construction came at the very end of the developmental sequence. Göbekli Tepe and Karahan Tepe break this model. The construction at both sites predates the agricultural revolution by approximately 2,000 years. The people who built them were hunter-gatherers. They lived in a region where the wild ancestors of wheat and barley grew naturally, and they ate gazelle and aurochs and pistachios and almonds. They did not farm, they did not domesticate animals at scale. They did not have pottery, they did not have writing, they did not have metal, and yet they organized themselves across multiple generations to quarry, transport, carve, and erect 20-ton stone pillars decorated with sophisticated artistic representations of the natural and supernatural world. Whatever cognitive and social capacity is required for that kind of project, hunter-gatherers had it. The order of operations in the traditional model is wrong, or at least incomplete. Now, I want to bring this directly into the conversation about whether we are the first civilization, because Göbekli Tepe is the closest thing we have ever found in the actual ground to a lost human civilization that predates the conventional starting point. It is not what the popular narrative describes. It is not Atlantis. It is not a metallurgical, technological, oceanic, navigationally sophisticated civilization, with knowledge that was carried into later cultures by survivors of a cataclysm. It is something stranger. It is the realization that complex monumental architecture, ritual sophistication, and transgenerational planning existed in human societies long before agriculture, long before settlement, long before everything the textbooks said you needed. The implications are sobering. If we missed something this big, this close in time, this well preserved, until the mid-1990s, what else are we missing? If the entire conceptual framework for the emergence of human civilization needed to be rewritten on the basis of a hill in southeastern Turkey, what other frameworks might need rewriting? The connection to the central thread is this. Real evidence of pre-conventional civilization, when we actually find it, almost never looks like the popular narrative. It looks weirder, more specific, more historically situated, more interesting in detail than the broad strokes of the popular story can accommodate. Göbekli Tepe is more interesting than Atlantis. It is also real. And the Silurian hypothesis would predict that any prior industrial or technological civilization on Earth, if it existed, would look stranger than our imagination wants to make it, possibly unrecognizably stranger. possibly so different in its development that we would not, even confronted with its remains, immediately understand what we were looking at. There is one more case I want to walk through before we leave the question of recent prior civilizations and move on to the distant past. It is the case of Gunung Padang. It is the case that shows what happens when an extraordinary claim runs through the methodological filter of mainstream archaeology, and the filter catches the claim, and the claim does not survive. The next part is the anatomy of a retraction, and it shows you what the system is actually for. Is less than break time equals 1s, is greater than number, part 10. Gunung Padang and the anatomy of a retraction. In 2023, a paper appeared in the journal Archaeological Prospection by Danny Hilman Natawidjaja, a senior geologist at Indonesia's National Research and Innovation Agency. The paper claimed that Gunung Padang, a stepped hill in West Java, was a pyramid more than 25,000 years old, making it the oldest known monumental structure in the world by a margin of approximately 20,000 years. Gunung Padang is a real archaeological site. It sits on top of a volcanic neck in the Cianjur Regency of West Java, Indonesia. The visible upper layer of the structure consists of basalt columns arranged in terraces, with evidence of human modification to the columns and to the terrace surfaces. This upper layer is conventionally dated to about 2,500 years ago, making it a moderately old but unremarkable example of indigenous Indonesian megalithic architecture. Natawidjaja's team, using ground-penetrating radar, seismic tomography, and radiocarbon dating of organic soil samples extracted from boreholes drilled into the structure, claim to have identified multiple distinct construction phases beneath the visible terraces. The deepest layer, they argued, dated to between 25,000 and 14,000 BCE, placing its initial construction in the Paleolithic, long before any conventional date for the emergence of monumental architecture. If the claim had held, it would have rewritten the history of human civilization more dramatically than even Göbekli Tepe had. A monumental structure constructed 25,000 years ago by a Paleolithic culture on an Indonesian island would have shifted every assumption about the cognitive and organizational capacity of Upper Paleolithic humans. It would have required entirely new frameworks for understanding the development of complex societies. The response from the mainstream archaeological community was immediate and detailed. The fundamental criticism was methodological. Radiocarbon dating of organic soil samples tells you when the organic material was deposited. It does not tell you when surrounding stone structures were constructed. If you drill a borehole through a stone terrace and find organic carbon at a particular depth dating to 25,000 years ago, what you have learned is that organic material from 25,000 years ago is at that depth. You have not learned that the stones above or around that organic material were carved or arranged at that time. The stones could be much younger. The organic material could have washed in from the surrounding hillside through cracks and channels in the natural rock. To date a stone structure, you need direct dating methods. You need to date the mortar holding stones together. You need to date charcoal that was deliberately placed inside the construction context. You need to date a hearth that was built into the floor of a structure. You need to establish an unambiguous stratigraphic relationship between datable material and the construction itself. Natawidjaja's team had not done this. The radiocarbon dates they reported were from organic soil samples in boreholes. The relationship between those samples and the proposed construction phases was inferred rather than directly demonstrated. The basalt columns in the structure were natural, not human-carved, and the orientation and arrangement could be explained by natural cooling and fracturing of volcanic rock. The seismic tomography signatures the team interpreted as evidence of separate construction phases could also be explained by natural variation in the underlying volcanic geology. In 2024, Archaeological Prospection formally retracted the paper. The grounds for the retraction were methodological. The dating could not support the claim made for it. The paper had passed peer review initially because the underlying data was real and the geophysical surveys were competently conducted, but the inferential leap from the data to the conclusion about ancient construction was, on closer examination, not defensible. Natawujaja's response to the retraction was vocal. He defended the work. He characterized the retraction as censorship by Western archaeological orthodoxy. He called for independent international research at the site. He gave interviews to alternative history outlets that framed the retraction as institutional resistance to extraordinary claims rather than as a legitimate methodological correction. The geological and archaeological consensus, however, settled around the view that Gunung Padang is a natural volcanic feature with human modification on its upper terraces dating to about 2,500 years ago. There is no Paleolithic pyramid beneath West Java. The connection back to the central thread is the most important point in this part. Distinguishing real anomaly from interpretive overreach is the entire methodological challenge of the Silurian question, scaled up by orders of magnitude. The Gunung Padang case showed the system working as it is supposed to work. A claim was made. The claim was evaluated. The evidence did not support the claim. The paper was retracted. This is what science is supposed to do. But for our deeper question, the same methodological filter is the problem. If a claim of pre-human civilization on Earth in the far past were made today, with the kind of evidence currently available, the same filter would catch it. The geological timescale community could not agree to formalize the Anthropocene with our own civilization in full operation. They would certainly not agree to formalize a hypothetical civilization 60 million years ago on the basis of indirect chemical signatures. The same conservative standards that protect us from premature claims also conceal anything that does not meet them. The Gunung Padang case is not evidence against the Silurian hypothesis. It is evidence that the methodological standards are working. It is also evidence that those standards, applied consistently, would catch and reject a genuine prior civilization claim almost regardless of the evidence, because the evidence required to support such a claim would be the kind of artifact that, by definition, does not survive geological time. We have, at this point, walked through the closer-in-time version of the question, the Younger Dryas, Göbekli Tepe, Gunung Padang. We have seen that even when the evidence is good, the question is hard. We have seen that real lost civilization discoveries look stranger than the popular narrative. We have seen that the methodological filter rejects claims that do not meet its standards, regardless of which direction the bias runs. And we have arrived at the moment where the far-past version of the question becomes unavoidable. The next part defines the window in which a non-human, pre-human civilization on Earth was even physically possible. It is a long window. It is hundreds of millions of years long. And what lived in it? What could have lived in it? And what we have learned about the boundaries of the question is the next part of the story. Is less than break time equals 1s? Is greater than? Number part 11. The Carboniferous floor and the Dinosaur window. To understand whether anyone could have preceded us on Earth, you have to start with the most important constraint on the question. No industrial civilization on Earth is possible without accessible fossil fuels. Without coal, oil, or natural gas at a useful scale, the energy density required for sustained industrial activity simply does not exist on a planet that has not been technologically modified. And without an industrial revolution, the chemical signatures we have been talking about, the carbon isotope excursions and the radioactive isotopes and the synthetic organic compounds, do not appear. Without the signatures, the civilization is, by definition, harder to detect even in principle. So when did Earth first have accessible fossil fuels in significant quantities? The answer is not as old as you might think. Land plants did not exist before the Silurian period, which began approximately 440 million years ago. The earliest land plants were small, simple, and did not produce significant amounts of recalcitrant carbon that could become coal. Plants did not really come into their own until the Devonian period, which began about 419 million years ago. The first forests appeared in the late Devonian. But the truly massive coal-forming forests, the ones that laid down the major coal seams of Earth's geological record, appeared in the Carboniferous period, which ran from about 359 million years ago to about 299 million years ago. The Carboniferous is named for coal, carbon, the period during which Earth's atmosphere was at its highest oxygen content, around 30%, where today it is 21%. The period during which giant insects could grow because oxygen partial pressure allowed it. Dragonflies, with wingspans of 75 centimeters. Millipedes, more than 2 meters long. Massive arthropods and amphibians moving through humid, swampy forests of fern-like trees and primitive seed plants. The reason the Carboniferous laid down so much coal is partly an accident of evolutionary timing. Trees had evolved the ability to produce lignin, the tough structural compound that allows woody growth. But the bacteria and fungi that would eventually evolve the ability to decompose lignin had not yet caught up. So when Carboniferous trees died and fell, their wood did not rot completely. It accumulated. Layer upon layer of partially decomposed plant material built up in swamps and basins, and over millions of years and great pressure, it became the coal seams that humans dug up in the 18th, 19th, and 20th centuries to power their industrial civilization. This gives us the hard flaw of the Silurian question. Any prior industrial civilization on Earth had to exist between roughly 350 million years ago and a few million years before us. Before 350 million years ago, no coal. Before coal, no industrial revolution. Without an industrial revolution, no detectable signature of the kind we are looking for. After a few million years before us, the window closes because the geological record is too well resolved to plausibly hide a major civilization that recent. That window is still enormous. 350 million years. Humans have had 250 of those years. The ratio of our occupation of the window to the size of the window is approximately 1 to 1.4 million. We could fit 1,400,000 human industrial civilizations into that window, end to end, with no overlap. What lived in that window? Let me walk through the major periods, because the answer matters. In the Carboniferous itself, you had giant arthropods, large amphibians, the first reptiles, and forests of lycopsids and ferns. None of these animals had the cognitive features we associate with the path to high intelligence. They had small brains for their body size. They had limited sensory integration. They had simple social behavior. The path to civilization, whatever that path looks like, does not seem to have been open through any of these lineages. In the Permian, which ran from about 299 to about 252 million years ago, you had large and diverse synapsid reptiles. The synapsids are the lineage that eventually became mammals. Some of the Permian synapsids were impressively large, with elaborate dorsal sails for thermoregulation and complex teeth that suggest active predation and herbivory. But again, brains were small. Behavior was, as far as we can tell from the fossils, reptile typical. There is no anatomical evidence for the kind of cognitive expansion that the human lineage shows starting around 2 million years ago. The Permian ended catastrophically. The Permian-Triassic extinction event, approximately 252 million years ago, was the largest mass extinction in Earth's history. Roughly 96% of marine species and 70% of terrestrial vertebrate species went extinct. The cause is debated, But the leading explanation involves the Siberian Traps, a massive volcanic province that erupted for about 2 million years and injected enormous quantities of carbon dioxide, sulfur compounds, and other greenhouse and acidifying gases into the atmosphere. The climate destabilized. The oceans acidified. Most of the biosphere died. If a civilization had existed in the Permian, the end Permian extinction is exactly the kind of erasure event the Silurian hypothesis describes. Almost nothing from the Permian biosphere survived. The fossil record from before the boundary is sparse compared to what came after. But the truth is, the Permian probably did not have the conditions necessary for a civilization. The biosphere had not produced the kinds of large-brained, socially complex animals that the path to civilization seems to require. The window was open in principle. In practice, nothing was walking through it yet. The Triassic, which ran from about 252 to about 201 million years ago, was the recovery period. Small early dinosaurs appeared in the late Triassic. The first true mammals appeared, all of them small, mostly shrew-sized. The first pterosaurs took to the air. The biosphere reorganized. By the end of the Triassic, the foundations of the Mesozoic world were in place. Then came the dinosaurs proper. From the late Triassic, through the Jurassic, and through the Cretaceous, dinosaurs were the dominant terrestrial vertebrates of Earth. Their reign lasted approximately 165 million years. That is more than 550 times longer than the entire span of recorded human history. It is more than 660,000 times longer than the human industrial era. What did the dinosaurs do with 165 million years? They diversified into every available terrestrial niche. They evolved feathers. They became warm-blooded, or partially warm-blooded. They built complex nesting and parental care behaviors. Some grew to be the largest land animals that have ever lived. Some became fast, agile, intelligent predators. They produced a biosphere that no terrestrial ecosystem since has matched in scale and variety. But did any dinosaur lineage approach intelligence at our level? The honest answer, based on the available fossil evidence, is no. The brain-to-body ratios of nearly all dinosaurs were low compared to mammals and birds. There is no evidence of tool use beyond the simplest functional behaviors. There is no evidence of complex social organization beyond what is observed in some living birds and reptiles. The dinosaurs were spectacular animals. They were not on the path that led to civilization. There is one notable exception in the analysis, and it is the part of the story that has fascinated paleontologists for more than 40 years. The Canadian paleontologist Dale Russell, who spent his career studying late Cretaceous theropods at the Canadian Museum of Nature, made a careful study of a small theropod dinosaur called Troodon formosus. Troodon was lightly built, fast, with binocular vision, opposable claws on the inner toes, and a brain-to-body ratio that was, by dinosaur standards, exceptional. Russell calculated that Troodon's brain-to-body ratio was roughly comparable to that of modern ratites, the large flightless birds like ostriches and emus, not human level, not even chimpanzee level, but higher than any other dinosaur Russell had measured. In 1982, Russell published a thought experiment. He asked what would have happened if the lineage of Troodon had not gone extinct at the KPG boundary 66 million years ago, if the asteroid had missed. If Troodon had continued to evolve along the same trajectory, Russell calculated that, given a continuation of the trend in brain expansion, Troodon's descendants could plausibly have reached primate-level intelligence within 20 to 50 million additional years. To make the thought experiment concrete, Russell collaborated with the Canadian sculptor Ron Seguin to build a life-size model of what an intelligent descendant of Troodon might have looked like. The model became known as the Dinosauroid. It was bipedal, with an erect posture, 3-fingered hands with opposable thumbs, a large head with a high cranium, and binocular vision. It was vaguely humanoid in form, although green and reptilian in skin. The Dinosauroid sat in a glass case in the Canadian Museum of Nature for decades, where it became one of the most photographed and most debated objects in 20th century paleontology. Russell himself emphasized that the Dinosauroid was speculation. It was a thought experiment about evolutionary trajectories, not a claim about what Troodon would have become. Most paleontologists who have responded to the Dinosauroid have argued that the model is too anthropocentric. It imposes a mammalian, human-like body plan on a reptile lineage that, even if it had evolved high intelligence, would more plausibly have retained features of the original Troodon body plan, including a horizontal posture, a balancing tail, and a non-humanoid skull architecture. But here is the part that gives the thought experiment weight. The dinosaurs had 165 million years. Mammals, since the KPG extinction, have had 66 million years, and in that time we have produced one lineage with our level of intelligence. The cognitive expansion of the human lineage happened in the last 2.5 million years, which is 1/26th of the time mammals have been the dominant terrestrial group. If high intelligence is achievable in 2.5 million years out of 66, then in 165 million years, it should plausibly be achievable many times over. So why no dinosaur civilization? The honest answer is, we do not know. There is no biological barrier we can identify that would have prevented it. The evolutionary trajectories of the dinosaurs simply did not lead to the cognitive expansion that the mammalian lineage produced. Whether this is because of bad luck, because of the specific selection pressures of the Mesozoic, because of constraints in dinosaur neuroanatomy that we do not yet understand, or because high intelligence is genuinely much rarer than it looks, we cannot say. What we can say is this. The KPG extinction at 66 million years ago is the closest historical example of a civilizational reset, even though no civilization existed to be reset. The Chicxulub asteroid, 10 kilometers wide, struck the Yucatan Peninsula. Tsunami waves the height of skyscrapers crossed the Gulf of Mexico. Wildfires burned across continents. Atmospheric ash blocked sunlight and crashed global temperatures. 3/4 of all species on Earth went extinct, including every non-avian dinosaur. The mammals survived because they were small, nocturnal, and able to live on the carrion and seeds of the post-impact world. If a civilization had existed in the late Cretaceous, the KPG event would have erased it. The chemical signature of that civilization would now be at the same boundary as the famous iridium spike that marks the impact itself. That boundary has been studied intensely for 45 years, since the iridium spike was first identified by Luis and Walter Alvarez in 1980. We have looked at the KPG boundary in dozens of sites around the world. We have measured its chemistry. We have studied its mineralogy. We have not found, in any of those examinations, anything that resembles the chemical signature of an industrial civilization. Whatever was happening on Earth at the KPG boundary, whatever the dinosaurs were doing in their last years, it was not building cars and burning coal. One more layer I want to add to the dinosaur question before we move on, because it relates to the central thread in an important way. The fossil record of dinosaur intelligence is not just about brain-to-body ratios. It is also about behavior. We know, from trackways and nesting sites and bone beds, that some dinosaurs lived in herds, that some practiced parental care, that some hunted in coordinated groups, that some migrated across continents. These are behaviors that, in modern animals, correlate with cognitive complexity. Some Cretaceous theropods, beyond Troodon, show signs of cognitive sophistication that would not have been obvious from brain size alone. What we cannot tell, from the fossil record, is whether any of these behaviors involve the kinds of symbolic thought, tool-making, or generational knowledge transmission that we associate with the path to civilization. Stone tools fossilize. Wooden tools and biological tools mostly do not. If a dinosaur lineage had developed a tool culture based on perishable materials, we would have almost no way to detect it. The absence of stone tool sites from the Cretaceous does not prove the absence of tool use. It proves the absence of stone tools that have survived in identifiable form. This is, of course, speculation. There is no evidence that any dinosaur lineage developed tools or symbolic thought at the level that would constitute a civilization. But the speculation matters because it shows the same problem the Silurian hypothesis points to. The kinds of evidence we can find depend on the kinds of materials that survive. If a culture used materials that did not survive, the culture is invisible to us. And the deeper in time we go, the more of the original signal is gone. The honest summary of this part is the following. The window for a prior industrial civilization on Earth is open in principle. The biology of the distant past does not require it. The geology does not record it. The chemistry does not show it. The absence of evidence is real. What remains unclear is whether the absence means no civilization existed or whether the rock simply cannot tell us. By the standards of the Anthropocene rejection of 2024, the answer is, the rock cannot tell us, even when there is something to tell. One question remains, the question that turns the entire video around, the question of what we, ourselves, are leaving behind. Because if we are not the first, the question of who follows us is no less urgent than the question of who came before. The last part is the inversion, the question of what we leave, the question of whether anyone who comes after us will know we were here, is less than break time equals 1s, is greater than number, part 12. The last question, what will be left of us? Every argument we have made so far about whether a prior civilization existed on Earth is also, by symmetry, an argument about whether we ourselves will be detectable in the distant future. Apply the Silurian hypothesis to the next 60 million years. Imagine the planet without us. Imagine the slow grinding of plate tectonics. Imagine the rain and the wind and the erosion. Imagine the rock cycle running its course. Imagine, then, an intelligence rising on Earth 100 million years from now, looking for evidence of what came before. What would they find? The estimates have been done. Paleontologists who have run the numbers based on average sedimentation rates and fossilization probabilities and the geographic distribution of human burials estimate that of the roughly 8 billion humans currently alive, the number whose remains will ever fossilize and be identified by a future paleontologist 100 million years from now is in the dozens, possibly fewer, out of 8 billion. Out of the entire current population of an entire global civilization, perhaps 50 individual skeletons will survive in conditions where future intelligence could find and recognize them. The remaining 7,999,999,950 of us will be, geologically speaking, gone. Compare this to Homo erectus, a species that lasted 6,000 times longer than recorded human civilization, left us, in 130 years of intense paleontological work, a few thousand identifiable specimens. Our descendants, if they go looking for us 100 million years from now, will have a thinner record from our species than we have from Homo erectus, less than 1,000th as much. They will know we existed only from chemistry, from anomalies, from inferences. They will not have skulls and skeletons and tools to study the way we have for our hominid ancestors. So what will they find? Let me walk through the most likely fossil indicators of the human industrial era in approximate order of detectability. Chickens. This is not a joke. Of all the species we have domesticated, the chicken is the one whose biomass has expanded most spectacularly under human management. There are approximately 25 billion chickens alive on Earth at any given moment. That is more than 3 times the number of any other bird species. Chickens are bred raised, and slaughtered at industrial rates, with the bones of slaughtered birds concentrated in landfill and processing site sediments at densities no natural process could produce. A future paleontologist sifting through late Holocene sediments would find an extraordinary global spike in Gallus bones, distributed across every continent except Antarctica, in concentrations that would be inexplicable as a natural ecological phenomenon. The chicken bone layer is one of the most distinctive features our civilization will leave. Plastic, a thin layer of synthetic organic compounds, distributed globally across marine and terrestrial sediments, persisting in chemically recognizable form for an unknown but possibly very long time. The exact persistence of microplastics in the geological record is debated, but some estimates suggest the chemical signature could last for tens of millions of years, even if the original polymer structures break down. The plastic layer would be the strongest direct chemical evidence of synthetic manufacturing, global metal redistribution. Lead, copper, zinc, mercury, and rare earth elements concentrated in geographically distinctive patterns that mining and industrial activity produce. The patterns would be distinguishable from natural ore distributions because they would reflect the locations of human industrial centers rather than the locations of natural mineral deposits. A future geologist mapping the metal anomalies would see, very clearly, that something had moved these elements around in patterns that natural processes do not produce. Long-lived radionuclides. Plutonium-244, with its half-life of 80 million years, will still be detectable in Crawford Lake sediments long after the lake itself has been recycled. The plutonium signature is the strongest single piece of evidence that our civilization was technological in a specific way. There is no natural source of plutonium-244 on Earth. Its presence in sediment is unambiguous. The carbon isotope excursion. Our delta carbon-13 value drop, faster than any comparable event in the recoverable geological record, will be visible as a sharp negative excursion in sedimentary cores, persisting for tens of millions of years. The species redistribution. Pollen records will show wheat, corn, rice, and other agricultural species in places they did not naturally grow. Bones of cattle, pigs, sheep, and goats will show up in concentrations and geographic ranges that natural biogeography cannot explain. Now here is the question. Will these signatures, taken together, allow a future intelligence to conclude with confidence that we existed? The answer, by the same standards that the Subcommission on Quaternary Stratigraphy applied to the Anthropocene in 2024, is uncertain. The chicken bones might be interpreted as evidence of a particularly successful natural population. The plastic might be interpreted as a strange but ultimately unidentifiable organic chemistry. The metal redistribution might be argued as a sampling artifact or a series of natural ore migrations. The plutonium might be interpreted as an unusual nuclear event in Earth's history. The carbon isotope excursion might be interpreted as another natural warming event like the PETM. Each signature, individually, has plausible, natural explanations or can be argued to be insufficient. The constellation, the combination of all the signatures appearing together at the right ratios in the right timing, would be the case for our existence. It would be a strong case, but it would not be a case that everyone would accept. Some future subcommission, with its own conservative methodological standards, might vote against formalizing the Anthropoid era as an official epoch on the grounds that the signatures, while real, do not yet meet the criteria for a defined boundary. The 2025 Earth Detecting Earth paper by Sheikh Frank and colleagues calculated at what distance our current civilization's technosignatures could be detected by an outside observer using present-day technology. The answer, when you read the paper carefully, is sobering. Earth's signatures span 13 orders of magnitude in detectability. The brightest signatures, radio emissions, and city lights are detectable from many light years away. The faintest signatures, atmospheric chemistry shifts, and microplastic deposition are barely detectable from inside our own atmosphere. Most of our signatures fall in the middle, detectable by a sophisticated nearby observer, invisible to a distant one. Apply this to our own geological future. The radio emissions will stop the day our civilization stops. The city lights will go out. The atmospheric chemistry will return to baseline within tens of thousands of years. The plastic will break down. The chicken bones will fossilize unevenly, with most of them dissolving. The metal redistribution will be partially erased by the same plate tectonics that erased everything else. The plutonium-244 will remain. The carbon isotope excursion will remain. A thin sedimentary layer with a precise chemistry will remain. That is what we are leaving, a thin band, a constellation of isotopes, a distinctive but ambiguous signature. The work of an entire global civilization, 8 billion people, 2.5 centuries of industrial activity, condensed into a layer of sediment that a future intelligence might miss, might dismiss, might argue about for decades before reaching no firm conclusion. We are the Silurians of whoever comes next. We are also the Silurians of whoever came before, if anyone did. We exist inside a question we cannot resolve, asked by scientists who built the framework specifically to point out that the rock does not give up its dead easily, and the silence in the sediment does not necessarily mean no one was ever there. The cosmic implication is, I think, the heaviest one. If we are difficult to detect from inside our own civilization, in real time, with all the markers we are actively producing, then we should expect the universe to be full of civilizations that we cannot easily detect either. The Fermi paradox, the question of why we have not found extraterrestrial intelligence given the apparent age and size of the universe, takes on a different shape when you realize that we are not even confident we can detect ourselves. The framework Frank and Schmidt built for the Silurian question is the same framework that is now being applied to exoplanetary technosignatures. The Shake Earth Detecting Earth paper is the inversion. If you can describe the signature of a civilization on Earth, you can describe what to look for on other Earths. And the answer the framework keeps giving back is that civilizations are hard to detect. Hard to detect on Earth across geological time. Hard to detect on exoplanets across light years. Hard to detect perhaps in any setting except the one we currently occupy, looking at the artifacts and bodies and books of our own immediate past. So I want to leave you with the question that the entire video has been building toward. It is not, in the end, the question of whether anyone was here before us. The question is what the geological record can and cannot tell us. And the answer, on the most honest reading of the science, is less than we would like. When we look at the rock beneath our feet, we are looking at our own future grave marker. The chemistry of our civilization is being written into sediment that has not yet been buried. The plutonium and the plastic and the chicken bones and the carbon isotopes are all being deposited in real time all around us. In 10 million years, those layers will be buried. In 50 million years, they will be deformed and metamorphosed. In 100 million years, they will be the thin band that someone or something might or might not find. When we ask whether anyone was here before us, we are asking whether anyone will know that we were here. The Silurian hypothesis is not a paper about Atlantis. It is not a paper about ancient aliens. It is not a paper about a hidden civilization somewhere under the desert. It is a paper about the limits of memory written into stone. It is a paper about what time does to civilizations, and about what civilizations look like when time is finished with them. And the answer the paper leaves us with, the answer I want you to carry out of this video and into the quiet of your own night, is this: we are alone with the rock, The rock is patient. The rock does not lie. The rock simply forgets. And whether we accept that what we are losing now is what someone before us already lost, or whether we believe that we are the first, the rock does not care. The rock will hold what it holds. The rest is silence.